Hi people. Hi. I just thought of quickly doing the recording instead of doing the class live because most of y'all had issues with the time. So I wanted to be very fair because doing the class live and half of them not there, and then taking that recording and then rather than giving that recording the next day or the following 2 days after, I thought of doing the recording early hand and giving it as early hand as possible so that you'd be able to watch the recording in your meanwhile. Like you already have 4 to 6 free now, so you want to watch the recording at that time. So I thought of doing this. Anyways, I'll do an online session. I'll be live. I'll do a live session and send you all a Zoom meeting link. Let's say at 9, somewhat like we'll do a live session at 9. We'll do a meet at 9 so that if you all have any doubts that you all have, you all can ask, right? So that's how things are going to be. So I thought of doing the recording to be fair to everyone. And yeah, in the last class, what we were discussing was we were discussing certain questions and we were implementing something called the Karnoff map, the K maps, right? You know, you can simplify Boolean expressions in two ways. One is according to what do you call the Boolean laws, the other one is according to Karnoff maps, right? So we were implementing all these Karnoff maps into all these questions. Okay, so here I'm not going to do the questions. Questions are going to be done in the class physically. Pointless doing it online. Instead, I'm going to start teaching you all another theoretical part that's very important in terms of logic gates, right? You call these as adders. What do you call them? You call them adders, right? What are adders? Now, you have to understand this. When you talk about computers, computers do have something that's really important within them, and that part is what actually makes a computer, right? What am I talking about? I'm actually talking about something called the central processing unit. Now, whenever there is something that is taken into the computer as input, that is taken into the computer as input, right? And the computer sends that input or the data at input to the CPU for processing. And after processing is when it becomes an output. And the processing is done by the CPU, especially when it comes to calculations, arithmetic calculations like, let's say, addition, subtraction, division, multiplication, something like these. It goes to the CPU, obviously, like every other data or instruction as input, it goes to the CPU. Inside the CPU, there is one component, an important component called the arithmetic and logical unit. Now, this component over there is actually a small circuit, right? Inside that circuit, you have a sub circuit, you can say, that can do addition and subtraction too, right? You call that circuit the adder circuit. Adder. ADDER, the adder circuit. This adder circuit is going to do something for you. What is it going to do? Right? It is going to allow the arithmetic and logical unit to do all mathematical additions. Right? So there's this circuit called adder that literally does addition, right? So that's that logical part. That's that logical component that's there inside the arithmetic and logical unit to do all these mathematical or arithmetic additions, right? What do you call that component? The component is called the adder. Adder does is a logical component that does addition inside the arithmetic and logical unit. A very important part, obviously. You all know addition and subtraction. Computer doesn't differentiate addition and subtraction differently, right? The addition of a positive number is going to be plus. The addition of a negative number is what is going to be a minus. Can you understand what I'm trying to say? When you add two positive numbers, it will increase the value. But when you add a negative number to a positive number, it will eventually decrease the value. But in both the situations, what are you doing? You are actually adding. As simple as that. So computer uses that only single circuit called the adder, and the adder is going to be used to add or do the addition operation. Simple as that. Okay, right. Okay, so that's what you're gonna learn today. That's what you're gonna learn today, right? Have a look at this. Have the tute with you. I'm gonna follow up with the tute. So have the tute with you. Right. Give me a minute. Right. 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 You need to understand these people, right? When you talk about the CPU, right? CPU has a component called the arithmetic and logical unit, right? So this component is what does all these mathematical or arithmetic operation, right? It's what it does. So when you talk all of these, when you talk about all of these uh, mathematical operations, addition is going to be one main part. Okay, so you all know CPU is also a circuit. Sorry, CPU is also a circuit, yeah. And inside the circuit, you have sub-circuits like the ALU and all. And inside the ALU, you have a circuit, a sub-circuit called adder. So adder is going to be that component that's gonna add things for you, right? So today we're gonna learn about a logic circuit, right? That's gonna do addition addition and literally subtraction too, right? So it's a logical circuit. Adder is actually a logical circuit that does the addition function inside the ALU. Is that clear? So we're going to learn about how adder, what adder, and how do you create an adder, right? How is the actual implementation of adders are, and all these stuff. But remember, adders are logical circuits inside the arithmetic and logical unit that perform binary addition. Is that clear? Is that clear? No, this down. This down. This down. This down. Right. What do adders do? What do adders do? Have a look at this. Adders are logical circuits. Adders are logical circuits inside the arithmetic and logical unit of the CPU, right? That performs that performs what? It performs binary addition. Binary addition. So remember that. Remember that. What adders? So you have this space where you can write the answer inside your tube. So there's a question called what are adders. So remember, what are adders? Adders are logical circuits that are inside what? Uh, the arithmetic and logical unit, right? And these circuits allow you to do binary addition. That is what adders are. Clear? Clear? Right. Once again, what are adders? Adders are logical circuits inside the arithmetic and logical unit of the CPU that performs binary additions. Is that clear? Yeah? All good? Right. Give me a minute. Okay. right? So that's what adders basically are, right? When you talk about adders. The next thing is, right, whenever you talk about adders, you have to remember for a fact that whenever you talk about adders, right, there are two types of adders. When you talk about adders, there are two types of adders, right? There are two types of adders, right? When you talk about the adders, there are two types. Adders can be of two types, right? Adders can be of two types. Adders can be of two types, right? Adders are going to be called half adders. There is one type of adder called the half adder, and the other type of the adder called full adder. There are two types of adders. Half adder and full adder. There are two types, right? What makes the difference between a half adder and a full adder? Have a look at this. For an example, what you're trying to do is, people, you're trying to create a circuit that could do addition for you. You already know all the gates. Okay, what are the gates that we learned? We learned about the basic gates, which are AND, or, NOT. And then we learned about the combinational gates, NAND, and NOR. We also learned about some exclusive gates. If you can remember, exclusive OR, exclusive NOR, XOR, XNOR, which I'm talking about. And we also learned about something called universal gates, right? Gates that can build the functions of all the other gates. Like you can make one gate work like the other gate. Okay, what are the two gates that can act like that? NAND gate can act universally. NOR gate can act universally. So this is what we learned, and we've learned whatever that's necessary. Everything, right? Everything that we need is learned. Okay. So what are we trying to do now? Have a look at this. Whenever you talk about half adders, have a look at the tune. What are half adders? A half adder is a digital logic circuit that performs binary addition of two single bit binary numbers. Okay, what does half adder do? Half adder performs, half adder performs addition of what? Addition of what? Two single binary inputs. Addition of two single binary inputs. An example, like let's say A is one input, B is one input, two single, so two single. Huh? For an example, it's like 1 plus 1. So this is one bit. This is actually one bit here, and this is actually one bit here. So that's what it means. It means it's the addition of two single binary input. So A is one input, there's only single, there's only a single binary. B is the other input, single binary. That's what it says. Two single. There are two what? Two means two inputs, A and B. A your input, B your input, right? A is one input, B is one input, and it says single binary. So there are two inputs, and in each of these two inputs, there's only a single binary digit. So here one, here one. So in additions like these, we are going to use half adder. So what does the half adder do? Half adder does the addition. It's a circuit that does the addition of two single binary inputs. So there can be two inputs, A, B, but in each of these inputs, there should be only one. In A, there should be one digit by one binary digit. In B, there should be one binary digit. Right? And when you add these two, you'll get an answer. So for you to do such two single bit binary addition, you have to use, or you can use, the half adder, right? But full adders are different. If you look at the tute, if you go to page number 5, or page number, yeah, page number 5, in the full adder side, you'll get to notice that full adder is the adder that adds 3 inputs and produces 2 outputs, which means it's like this. What does full adder do? It does the addition of right? 3 single, there you go. Now, how many inputs can you take? three. You can get three inputs. In a half adder, you can take only two inputs. But in a full adder, you can take three inputs. It's an addition of three single binary digits, right? You add three single binary digits, produce, and you produce two outputs. That is what you call half adder. The circuit that can take three inputs. Now, over here, if you actually focus on this part here, focus on this part here, you get to see only yes, you get to see only A and B. A and B getting added, two inputs. Two inputs get added, you get two outputs. What are the two outputs? Zero is one output, one is another output. Right? In full adder, it's not like that. You're gonna do three. You're gonna add three things. You're gonna add three things. Have a look at this. Three inputs. Three inputs. Have a look at this. Have a look at this. For full adders, it's literally like this. You're gonna take three inputs. A, for an example, A, B, C. It's like you adding something like this. One, one plus one plus. Oh, get me. Like it's like this. You're adding three inputs. You're adding three inputs. Okay, I hope you know binary addition. I taught you all binary addition. You're taking in three inputs, no? Three inputs, no? Have a look at this. One plus one in terms of decimal is three. Three when you convert to binary, because you're doing binary addition here. Three when you convert to binary, you'll get 1. Have a look at this. What does the full adder do? It does the addition of three single digits, which is A, B, C. It can take in three inputs. But when it produces only two outputs. Look at the two. This is one output. This is one output. So full adders, what do full adders do? They basically take in three inputs. They add three inputs, three single binary digits, and give you two as the output. Clear? All good. So that is what a half adder and a full adder is. Now these are circuits. So what we're gonna do is we are gonna find circuits. We're gonna draw circuits. Now that's what the lesson is all about. And you people are uh, like people who create computers, circuits. That's how you should be thinking. You're on the hardware level now, right? You're dealing with ones and zeros. You're like that computer operators, the ones who create circuits, the one to create all these hardware. So that's how you have to think. So you have a task now. The task is to create a circuit that can do addition of two single binary inputs and the addition of three single binary inputs. Right? So we're going to make circuits for each of these. Most importantly, today I'll be discussing about half adder only. Okay? All good? All clear? Right. Because full adder requires physical teaching. So I'm going to do half adder today. Okay? Right. Right. Nice. Right. Get this noted on your writing book. Get this noted on your writing book. Get this noted on your writing book. Full adder, half adder. By presenting this. Okay, have a look at this. I hope you could see the screen now. Have a look at the screen. This is what I wrote. So adders are logical circuits inside the arithmetic and logical unit of the CPU that performs binary addition, right? Uh, Whereas when you talk about adders, there are two types of adders, half adder and full adder. What does the half adder do? Half adder is the addition of two single binary inputs, whereas a full adder is the addition of three single binary digits. This is what I was talking about. If you have a look at this, you'll understand, right? A and B over here, A and B over here. What is A and B over here doing? Let me right. A and B over here. If you look A and B over here, A is going to be, wait, it doesn't allow me to point. What's the pointer? Whiteboard. Okay, I'll give you some time. Note this down. Now, meanwhile, you will have to okay. Meanwhile, you'll have to remember this. Whenever you talk about half adder is the addition of two single binary inputs, which means you have two inputs. But in both the inputs, you can have only single binary digits, so two single binary digits, and then it will give an output. That's what half adder does. Full adder is different. Full adder is the addition of three single binary digits, which means it can take three inputs. But in all of these three inputs, you should have only one single binary digit, and it will produce two outputs. Addition of three, two outputs. Addition of two, two outputs. So these are the two types of adders. So very mainly, we're going to talk about half adder today. All good now? Right. Nice. Have a look at this. Right. But I hope you can see the whiteboard. Yeah, it is possible. It is possible. I'm going to push this aside a little bit. I'm going to push this aside a little bit. And I'm going to use this space over here now. Side. Right. Have a look at this. Right. Page number 4 into half adders. Whenever you talk about half adders, right? Whenever you talk about half adders, this is what you have to remember. So, what are we trying to do here in terms of half adders? If you can actually understand what we are trying to do in terms of half adders are, we are trying to add two inputs, two binary inputs, and get two outputs. Right. Have a look at this. What could be the possible combinations if you look? Now, I'll write all the combinations, right? We are trying to create a circuit now, right? And we know all the gates. So, by combining all these gates is when we can create a circuit, right? You all know that for a fact. Have a look at this. A is one input, B is one input. Let's say these are the two inputs, right? That can be first, there can be something like this. Let's say you're adding uh, 0 with 0, the two binary numbers. The other situation, A, B, 0 with 1. The other one, A, B, 1 with 0, right? The other one, AB, 1 with 1, right? Now, what you're supposed to do is you're supposed to guess out the answers first. The answers first. Remember, what do half adders do? They do the addition of two single binary inputs, right? Right? They do the addition of two single binary inputs and they give the output of 2. right? That's what has happened. So even in the previous stage over here, even in the previous stage over here, even in the previous stage over here, you get to see, and have a look at this. You get to see, look, you get to see what do you call A being one input, B being one input, addition of two single inputs, and you get two outputs. This is one, the zero is one output, and the one over here is one output, right? So that's what our main goal has to be. Whenever you're drawing a circuit, whenever it's a circuit, right, it's going to be this, right? Addition of two. If it's half a Hz, you're going to add two single inputs and get two outputs. Have a look at this now. 0 and 0. When you add 0 and 0, when you add 0 and 0, what would be the output? Obviously, you need two outputs, huh? Two outputs. It's going to be 0 and 0. Right? No, let me use a different color. 0 and 0. Right. Have a look at this now. 0 and 1. When you add 0 and 1, what would be the answer? It will be 1, 0. Binary addition. Binary addition. When you add 1 and 0, it will be again 1 and 0. Right? Right? And when you add 1 and 1, you add 1 and 1, right? Remember, 1 and 1, when you add in terms of decimal, it's 2. And 2, when it's converted to binary, it's actually 0, 1. Okay? Okay? Right? Now listen to this carefully. You're creating a circuit. Huh? You're creating a circuit. You are creating a circuit. And you will have to agree with this fact. Look at this. You are trying to take in two inputs into the circuit and give two outputs out, right? Your two inputs are going to be A and B, right? Your two outputs are going to be this and this. Now here, when you add 0 and 0, when your input at A is 0 and when your input at B is 0, your outputs are, one output is 0, the other output is 0, right? These outputs have a name. Like these inputs having names, like one input is A, right? The other input is B. No? Similarly, the output also has names. Have a look at this. Whatever that I've written in black, whatever the output that I've written in black, this side, you call this output as, the sum. What do you call this? You call this output as sum. Okay. Meanwhile, the output here is called, carry. So whatever you write, whatever written in red is called carry, and whatever written in sum is black is called sum. So that's how it is for everything over there, right? Right? So this is a sum, and this is carry. This is again sum, and this is again carry. Sum and carry. You need to understand this. These are names that are given, na. Input එකට A B කියලා නමක් තිබ්බොත් ඉතින් outputs එකටත් තියන්න ඕනේ. ඒක නේ. Yeah, true නේ. So yeah, if one input is A, one input is B, outputs also should have some way of identification. That is why you call the most what do you call the most right bit, the sum, and the most left bit as the get. Okay, okay. I hope these are clear now. Now the job is not done. The job is definitely not done. What you should be doing is let me present this for a while. I don't know how this thing. Okay, have a look at this. Pan puts some carry. These yeah, some carry. This is called some carry, and yeah, some man carry. Okay. Okay. Right. I hope. Yeah. The job is not done yet. You're supposed to draw the circuit. You're supposed to draw the circuit. But to find the circuit, to draw the circuit, you need to identify the gates in the first place. Hari, Balamugu. Listen. Let us identify the gates. Right. Okay. Think of all the gates and tell me this. Think of this. You can't tell me it's a recording. But yet, yeah. Okay, Josie, think. What could be the gate? If you look at the first example here, if you look at the first example here, what could be the gate that will give the output of 0 at sum when A is 0 and B is 0? What could be the gates? When both the inputs are zeros, the output is 0. What could be the gates? When both the inputs are 0, the output is 0. What could be the gates? What could be the gates? It can be anything, no? It can be anything, no? It can be and, it can be or, it can be not cannot be there. You can't take not only takes in one input, and or can be taken. Can you take NAND? NAND you can't, no? NAND you can't, NAND you can't, NAND you can't. Nor can you take nor also you can't, nor also you can't. So here at some, what could be there at some? What could be there is you can talk about and or. What about carry? Carry is also the same, no? To get the output at carry, if A is, what could be the circuit that gives the output of 0? When A is 0, B is 0, same. It can be and, it can be or. Now look at this situation. We are trying to figure out the gates, huh? Right? In the situation, in the gate, or in what situation, what gate could be the perfect gate? Because you are trying to draw the circuit. You're trying to figure out the circuit. To figure out the circuit, we should know the perfect gates that give the perfect output. Have a look at this. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. If 0 and 1 are given as input into a gate, what gate gives the output of 1? What could be the gate at sum? We have to think. Can the AND gate give the output of 1? Can the AND gate give the output of 1 when 0 and 1? No, AND can't. Can OR give? Yes, OR can give. OR can give. True. Which means we have to remove AND from all our options. So at the sum place, we understood that AND won't come. Right? It cannot be AND because if we are using AND gate, there 0 and 1 should give the output of 0. But eventually it's not AND there. It works like the OR. So we figured out that it's OR. Up to this point, I'm not saying it's right. Okay, up to this point. Meena, look at this. Look at the carry. Look at the carry. Look at the carry. 0 and 1. 0 and 1. 0 and 1. What gate gives the output of 0? Okay, over here you can say OR gate will not give the output of 0, but you know, AND gate will give the output of 0. Right? So in this place, you can understand that you can cancel off OR from the options at the carry. Right? So as of now, we understood to get the sum, we need the OR gate. To get the carry, we need the AND gate. Okay? To get the sum, we need the OR gate. And to get the carry, we need the AND gate. We've identified that, but that's not right. That's not right. Go to the other options. Have a look at this. 1 and 0. 1 and 0. 1 and 0. What gives the output of 1 when it's 1 and 0? True. It's OR. Ah, nice. It's working. No, it's working. Don't get fooled. Don't get fooled. Don't be too soon to judge. Right. Carry? What about carry? What gate will give the output of 0 when 1 and 0 are the inputs? And don't get fooled. Don't get fooled. Don't judge too early. Have a look at the next one. Have a look at the next one. Here you get to see A being 1 and B being 1. When both the inputs are 1, the output should be 1 at sum if it was OR gate. But when both the inputs are 1, the output is 0. Bro, seriously? Can we use OR gate then? Can we use OR gate then? No. You can't use OR. You can't use OR. You can't use OR because it does not match with everything. It's not comparing. I mean, when you're creating a circuit, it should be a true one. It should be compatible with everything. Everything. Am I over here? Is it? Is it compatible? No. But we have a gate. that works like this, and we haven't even thought about it as of now. What is it? There's a gate called exclusive or you can call it XOR. How does the XOR gate work? RR, if you can remember, the number of inputs as ones should be odd. That is when the output is 1. Here, how many ones are there? There are 2. So, when you count, it's 2. When you count, it's 2. The count is an even count. Whenever it's an even count, the XOR gate will give the output of 0. But whenever it's an odd count, the XOR gate will give the output of 1. So, that is what happened in the previous thing also. If you look at the previous thing also, here you had only 1 1 is an odd count. Therefore, it gave the output of 1. So, here, or never, it should be XOR. Here also it's not OR, it's XOR. Here also it's not OR, it's XOR. Look at carry. Look at carry. Look at carry. If A and B are given as input, the output is 1 into that gate. What gate? Yeah, that is correct. That is fine. What gate is that? And gate. Okay. 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 All good. All good. So we figured out if we take two inputs as A and B to get the output at the sum place, we need to use the XOR gate. To get the output of AND place, sorry, the carry place, we need to use a AND gate. And this is more than enough for you to create the full ladder circuit. Have a look at this. So what did we figure out? What did we figure out? What did we figure out? We figured out, right. To find the sum, what do we use? We use what gate? To find sum, we use the XOR gate. To find the carry, let me erase this, let me make it nice. To find the carry, we use the AND gate. So we figured this out. All good? All clear? Yeah. Right. So there's a blank then page number 4. It says a half adder can be implemented using blank and blank gates respectively. Okay. So how can you create a half adder? You can create a half adder by using the XOR gate and the AND gate. Can you understand that? You can create the half adder. You can implement the half adder using the XOR and the AND gate. Can you understand that? Is that clear? Is that clear? Is that clear? So you can create, once again, you can create a half adder using XOR gate and the AND. XOR for sum and AND for the carry. Is that clear? All go, that's about half adder, right? The next thing that we're going to do is we're going to draw the circuit. Have a look at this. Circuit for the half adder. Circuit for the half adder. We know what the gates are. 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 I'm going to draw the circuit. Right. Have a look at this. Okay. Let's say I'm going to draw the circuit. I'm going to draw the circuit. Right. I'm going to draw the circuit. Have a look at this. Oh, wait, sorry. Have a look at this. In case, right, you're getting, what does half adder do? Half adder takes in two binary inputs. So let's say A is one input, B is one input. Right? A and B. What am I doing? Right. To find the sum, what should we do? We should take in A, we should take in B into what gate? We should be taking into what gate? The XOR gate. How do you draw the XOR gate? This is how you draw the XOR gate. I'm not good at drawing, I know, but this is how XOR gate is. Clear? Clear? Right? So this is where you find the sum. When you input the two digits that are at A and B as inputs, right, you'll get the sum. How do you write? What would be the Boolean expression here? A XOR B. Meanwhile, the next thing is what? You have to put A and you have to put B into what gate? A and B should be put into what gate? A and B should be put into A and B should be put into the AND gate to find the carry. Right? So here what do you have? You have A dot B. This is the half adder circuit. Simple, easy, no? All good, no? Understood this? Understood this? Right. This is what I would have explained in the physical class as well for today. Was this clear? Was this clear? Was this clear? Now you can draw the truth table. Huh? You can draw the truth table. How do you draw the truth table here? You have two inputs. What are the two inputs? A and B are your two inputs. What are your outputs? What are your outputs? If A and B are your two inputs, what are your outputs? One is a sum output. It's A bar. Sorry, not A bar. Huh? It's A XOR B. What's your other output? A dot B. In page number 5, you have the truth table to be drawn. So get that done. Huh? So you're gonna put 4 columns like this and draw the outputs. You all know the inputs. A can be, so B can be 0, 1, 0, 1. Is going to be 0, 0, 1, 1. And you know how XOR gate works. Based on that, put the outputs. You know how AND gate works. Based on that, put the outputs. Simple. This is what I would have taught today. So this is what I thought of completing today as well with the past papers, but with the question that are there in the table, but then eventually pointless now. Explaining all those questions online, I want it physically to be done. The other thing, I mean, I'm doing this recording. You're supposed to look at the recording. I know today don't be like 4:15 to 6:15 no class, and then like be like, oh, okay, I'm not gonna see this. I'll see this just before I come the next week. Don't do that. No, most probably, I would be sending a paper. Huh? I'd be sending a paper after the session, not after the session by let's say 9. Okay, a small paper testing whether you know all of these. Okay, so get ready. Sometimes I'll have a doubt clearing session, or else you can drop down all your doubts by WhatsApp. Obviously, I'll explain. Okay, na? Okay, na? All good, right? Okay, then that's it. This is what I wanted to cover. I hope you all understood what half adders are. Sorry, I have a presentation to be done now. I'm recording this at 9 in the morning. So yeah, so that again, I'm going to the university. That's a 4 hour presentation that I have to do. 4 hour presentation that I have to do. So it will be from 2 to 6. Uh, yes, so it's an important presentation, and that's why I couldn't do it. That's fine. That's fine. That's it. Okay, then. Take care. God bless you. See you in the next class, huh? Physically, definitely physically. Right. Okay. Bye. Bye.